I am happy to have Automotive Seminars as a sponsor for the show. Now, if you're not familiar, Automotive Seminars is a diagnostic technician training company. They've got a website that there'll be a link to in the show notes. And what they offer is top-notch training to technicians like us in the field. I've been taking their training courses for years and have got a ton of benefit out of it. They've got top-notch instructors, John Thornton, Scott Shotton, Scott Manna, and every other month they've got a 2-night course that you can sign up for. Join in, ask questions, and afterwards, you've paid for the course, you can access a recorded version whenever you want. You can rewatch the class 2 years later in case you wanted some details on it, and that is a fantastic feature. So make sure to check out the website to see what courses they have available and what's coming up in the future. This podcast is brought to you by Jarhead Diagnostics. Jarhead Diagnostics manufactures in-house diagnostic equipment and storage solutions, as well as distributes for companies like Pico, ATS, and TopDon. One of my favorite tools that I've bought from Brandon and Jarhead Diag is the case for the U-Scope. If you don't have a U-Scope, you probably should, but if you have one, you got to get one of these 3D printed cases, has a magnet on it, has a full-size BNC lead that you can connect to, and it gets rid of the weak point of that scope, which is the mini BNC connection, which is pretty fragile. This case makes this thing nice and secure and makes it an even better tool than it was. So check out jarheaddiag.com. The link is in the show notes. This episode is brought to you by L1 Automotive Training and Keith Perkins. If you're looking for education on module programming, J2534, EEPROM work, key and immobilizer, electrical diagnostics, or drivability diagnostics, Keith has a website, l1training.com, that's got over 60 hours of training videos on all those subjects and more. When I first started out doing mobile, I utilized Keith's videos on module programming in J2534 in order to get my head wrapped around what I would need for the tooling, the computers, the software setups, what kind of obstacles I would be up against when I'm out there programming modules on cars. And it was a huge benefit to me. And I continue to use the training videos that he has on his website. So I strongly recommend checking out l1training.com. We have got Auto Rescue Tools and Isaac Rodell as a sponsor for this podcast. Hey guys, if you're looking for programming laptops, you want the laptop set up ready to go for programming control modules on vehicles, you need key cutting equipment, you need diagnostic tools, Isaac is your guy. Has all that stuff available for purchase, and the support that he offers along with the purchase has been outstanding. I bought some stuff from him in the past. I got my Dolphin key cutting tool from him several years back. And again, the support has been phenomenal. Helped me out along the way with anything additional I needed to make it work for me. Also, for the month of June 2023, they've got Autel updates for sale. So make sure to check that out as well. Again, that's autorescuetools.com. The link will be in the show notes. Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. Hey, what's going on, automotive world? Welcome to another episode of the Automotive Diagnostic Podcast with me, Sean Tipping. It's just me today. You're stuck with me. But we're going to be covering an automotive sensor per request in the Facebook group, so I appreciate that. Before we jump into this today, I did want to make a recommendation for everybody. If you're looking for more content, another podcast to listen to, check out Matt Fonslow's new show. He's got 3 or 4 episodes out, Diagnosing the Aftermarket A to Z. with Matt Fonslow. You can find that on pretty much any podcast app that you use, probably the same one you're using to listen to this episode. It's got one episode with myself. I joined as a guest, but he's got some really great content, not only out, but coming out as well. I spoke with him some of the episode ideas. Obviously, super smart guy. You know, you all have listened to the podcast. You know that he's a very intelligent person. And I'm always interested to hear his thoughts. So we're going to get to be able to do that more often now with his own show. So I just want to make that recommendation to everybody to go check that out if you're looking for some more content. But with that out of the way, let's jump into today's episode. Today, we're going to be covering an automotive sensor, again, per request on the Facebook group. So I appreciate that, number one. If you've got something you'd like to hear about, please let me know, and I'll do my best to either share my knowledge and experience, which I'm going to do today, or get somebody else on here that can help me out with it that's more of an expert than I am. One of the best things I've learned about doing this podcast is how many incredibly intelligent people are out there that are willing to share their knowledge. And, sometimes all you have to do is ask, and you can learn a lot if you're willing to ask and listen to some of these people. So I know you're out there if you're listening to this and I'm giving wrong information or incomplete information on something, please feel free to reach out, and heck, I'll have you on the show and talk to you about it. I'm interested in that. I want to know that. But today I'm going to give you my best interpretation and understanding and experience of a wideband oxygen sensor. These are also known as air-fuel ratio sensors, two different names for the same component. They've been used for a long time. This isn't necessarily anything new. We go back to the 90s and we see them used in certain applications on Asian vehicles. But depending on the brands that you're familiar with, these actually might be fairly new. If you work on, I'm trying to think of an example here. Well, GM vehicles, for instance, it's not that they don't use these, but for a long time they didn't. And if you're in the aftermarket and you're just starting to see some of these in your bay, this still might be pretty fresh for you. Or maybe you've seen these and maybe you've replaced one, but you've never really dove into, how do I diagnose this sensor? How does it actually work? Which is, of course, the first step into diagnosing it, is understanding how it works. Now, on that note of understanding how a wideband oxygen sensor works, I think it is imperative that you understand how a narrowband oxygen sensor works before you jump into the wideband. Okay. Now, I have a little bit of information there to help you if you're not totally familiar with how a narrowband oxygen sensor works. There's a lot of information out there, but I have an episode 33 with John Gillespie. He joined me to talk about the nuances and the details of how an oxygen sensor actually works, a narrowband. So check that out if you haven't already, give you a refresher and get you up to speed to jump into a wideband sensor. Because in fact, some of our wideband oxygen sensors actually have a narrowband sensor inside of them, essentially, and they're going to function based off of the operation of a narrowband. So again, understanding a narrowband sensor will help you understand a wideband. But with that out of the way, let's jump into these sensors, how they operate, and what we can look at as technicians to help us diagnose, is the sensor failed? Is it functioning properly? How can we utilize this sensor in other diagnostic areas as well? So first things first, what's the difference between this and a narrowband oxygen sensor? Well, visually, there may not be a whole lot. You might not be able to tell this just by looking at the sensor. Of course, they're located in the same position, particularly upstream of the catalytic converter. I haven't personally seen a vehicle that had a downstream wideband. Not to say that they're not out there, they probably exist, but normally I see the widebands upstream of the converter and the narrow bands downstream of the catalytic converter, which again points out the fact that as technicians, we have to understand both sensors at the same time, essentially, because there are points where we're going to be comparing a narrowband to a wideband sensor. So you have to understand the difference in operation between the two. But
going back to what I was making the point about is visually you may not see a difference between these sensors. Now you could, if there's 5+ wires, it might be visually obvious that this is not a conventional narrowband sensor, but they may look identical. So in that case, you're going to be referring to either service information or some of the scan tool data that we're talking about. But how about operation? What's different about these two sensors, a narrowband and a wideband? Because essentially they're going to be doing the same thing. They're going to be measuring oxygen concentration in the exhaust, and in parentheses there, I could include when in the presence of combustible gases, but we are measuring oxygen content in the exhaust. And the reason that both sensors are going to be doing this is to determine the air-fuel ratio that happened inside the combustion chamber. Right? We have oxygen and hydrocarbons entering that combustion chamber, and we're going to rearrange atoms, essentially. We're going to rip those hydrocarbons apart, oxidize them, turn it into water vapor, carbon dioxide. Maybe we have some stuff left over that we don't want, but maybe there's oxygen left over that didn't get used. And measuring that oxygen content in the exhaust is one of the best ways that we can, or the engine computer can determine what was the air-fuel ratio going into that combustion chamber, right? And again, going back to what's the difference between these two sensors, they're both doing the same thing. They're both measuring oxygen content in the exhaust, okay? For that reason, to determine the air-fuel ratio of what happened in combustion. It's just that a wideband or an air-fuel ratio sensor, two different names, same component, so I may flip-flop on the names, but just get used to it, because if you work on multiple brands, you're going to see both those names and even more. Ford's is a universal exhaust gas sensor, something like that. They change it up depending on the brand, but again, same thing, wideband oxygen sensor. It's going to do it more accurately than a narrowband. It's going to be able to measure this more precisely within a larger range, hence the wide band, as compared to a narrowband sensor. And that's really the biggest difference between these two sensors, is that one is going to be more accurate at measuring that oxygen content in the exhaust than the other. So with this sensor, be it a narrowband or a wideband, what this is for the engine computer, and I think this is important to understand, this is the ECM, or the engine computer's way of checking its work as far as, did I add the correct amount of fuel? So think about this. Every other sensor under the hood or on the vehicle for the engine computer is there to tell the engine computer how much fuel to add based on the amount of air that's entering the engine, right? The amount of air that enters the engine, well, yeah, we can control it with an electric throttle and maybe some variable valve lift. It's much more difficult to control the amount of air that enters the cylinder. Really, we're just kind of measuring it and quantifying the air that's going in, and then we're going to match the fuel to it. That's the job of the engine computer. And it does this through the fuel injector, right? We have a electronically controlled fuel injector with hopefully a specific amount of pressure behind it, and the computer has a program designed to add a specific amount of fuel, a very precise amount of fuel via pulse width modulation to match to the air going in, right? So if we think about it as a math equation, we have X amount of air, which is 21% oxygen. Now we're going to add X amount of fuel or hydrocarbons to that mixture to hopefully get the proper ratio. And all the other sensors are dedicated to figuring that out. Well, maybe I shouldn't say all, but as far as engine operation goes, right? Our fuel tank pressure sensor's not involved, but I don't want to get too far in the weeds here. But like our mass airflow sensor, our MAP sensor, our crankshaft sensor, our camshaft sensor, intake air temp sensor, coolant temp sensor, right? All of those are inputs to the ECM to tell it how much fuel to add. And then ECM is going to do that by spraying the injector for a certain amount of time. We're going to match the fuel to the air that entered the cylinder, hopefully. But after that, there's really nothing else except for our oxygen sensor. It's the only sensor after the fact, after combustion, that tells the ECM, how did I do? Did I add the correct amount of fuel? Did I add too little? Did I add too much? What happened after I sprayed that fuel? Because the ECM is essentially blind after that point. It's going to spray that fuel, and hopefully it turned out right, but maybe it didn't. There's so many factors that can affect that. I'm not even going to go into all that right now. I'm sure you're aware of many of them, but this oxygen sensor or wideband oxygen sensor is there to let the ECM know how it did. It's there to check its work as far as adding fuel for combustion. That's the purpose of this sensor. And again, the reason of a wideband sensor is to do that more accurately, to do that within a wider range, to be more precise for the ECM. And it all comes down to emissions, right? It all comes down to what's coming out of the tailpipe and how much fuel is being consumed by that engine. I mean, we could run an engine without an oxygen sensor. And we do, cold start. If we go to narrowband stuff during hard acceleration, we're going to not even observe the O2 sensor. There's plenty of times. I think I've told this story on the podcast before, but I had an old Ram Charger that was from Mexico. We put an engine in it, and this guy came back saying his fuel economy was garbage. Well, hey, dude, it's an old Ram Charger. What do you expect? Well, we looked into it a little bit more. This thing didn't even have an oxygen sensor. However it was constructed or wherever it was constructed in Mexico, they had just spliced in the signal wire for the O2 into a 5-volt reference, and it defaulted to open loop all the time. Well, I mean, in all reality, this thing ran great, but he was right. It got garbage fuel economy, even considering that it was an old 318. But we actually added on an oxygen sensor. We cut a hole in the exhaust. We welded on threads. We inserted the oxygen sensor, wired it up to the ECM, and the ECM, surprisingly enough, came to life as far as that circuit went, started observing the O2 sensor voltage and went into closed loop, right? And what I'm getting at there is the engine computer can run without one of these things, but if we're trying to obtain the best emissions, the best fuel economy, this is there to correct the work of the PCM. Say, hey, you didn't quite add enough fuel here. Or, whoa, you're adding way too much fuel here. Let's adjust via fuel trims, okay? And again, backing up because I'm kind of going off into theory on engine operation, both these sensors are doing that. It's just one does it better than the other. That's the biggest difference between these two. And if we want to get more technical about the details there, a narrowband sensor can't really tell the ECM how rich or how lean its mixture was. And I may say rich or lean exhaust gases, and I realize that's not necessarily the case. It's all about O2 concentration, but understand what I'm trying to say there. It can tell if the exhaust gas that it's measuring is rich, or is it lean, or is it stoic, but that's pretty much it. It's kind of like a rich, lean switch more than it is a true sensor that can detect within a range. And again, I understand that there's a voltage range from 0.1 to 0.9 of a narrowband, but either less or more voltage doesn't correlate to a specific air-fuel ratio. Whereas in a wideband sensor or an air-fuel ratio sensor can actually precisely measure what was the air-fuel ratio going into that combustion chamber based off of what's in the exhaust. It can give the ECM an exact number. Again, within a range, it has its limits, but it's wider, of course, wideband oxygen sensor. It is wider than our narrowband sensor. Okay, this is the way I like to think of fuel control compared to these two sensors. And I'll be honest here, I got this analogy from a training event a long time ago, and I wish that I would have written down who this was from so that I could give them credit, and I honestly don't remember. And I was writing this down in my notes for this show, and I'm like, boy, I'd really love to give credit to the trainer that laid out this analogy for me. So if it's you, if you happen to be listening, or if you've been to a training event and you heard somebody say this, please let me know, because I'd love to give credit to this, because this is a great analogy. Really helps you think about how these sensors operate. But anyways, I'm going to get into it here. Think about walking down a long hallway, okay? And your goal is to get to the end of the hallway. Okay, very easy. Now, The problem is you are blindfolded. Okay. So somebody put a blindfold on you and you need to walk down this long hallway. You need to get to the end. And this is the ECM is you, right? The ECM has a blindfold on and the ECM is trying to run it stoic. Okay. That's getting down the hallway. That's right. Walking right down the center of the hallway and getting to the end. We're running it stoic. We have the perfect amount of air to fuel ratio and nothing extra left over that we don't want. And for us going down the hallway, we're just trying to get down the hallway. Now, because we're blindfolded, we're going to walk and eventually we're either going to go to the right or the left a little bit and we're going to bump into a wall either on the right or left side of us. Okay. So we walk, we hit the wall on the right side and we say, okay, this is our indicator that we've gone too far, that we're going in the wrong direction. Let's correct. So you would turn to your left to try to get back to center. Well, you keep going. And since you're blindfolded, again, you can't see where center exactly is. So eventually you hit the left side wall. Okay, I just hit the wall on my left. And so now I'm going to correct again, go back to the right. Eventually you'd hit the right wall, left wall, right wall, left wall, right? And you're just correcting based off of when you hit a wall. You don't know exactly where you're at within that hallway, though. That's the problem. And that's what an ECM is operating fuel delivery off of, using a narrowband oxygen sensor. Okay. It doesn't exactly know where it is as far as air fuel ratio goes. It's just getting those bumpers at either a rich or a lean. Okay, I'm lean, let's add fuel. Okay, I'm rich, let's take fuel away. And we're going to go back and forth over that line. And that's a narrowband oxygen sensor operation. And that's how those computers will operate. Now imagine the same scenario. You're going down the same hallway. You're still blindfolded because the ECM still really can't see what happens after combustion. But now instead of just relying on the walls and bumping into the walls, you've got somebody that's talking in your ear that can see and is telling you exactly where you're at within that hallway. And it may say, okay, you're about 6 inches from the right wall, go the other way. Oh, you're about 12 inches from the left wall, go the other way. And you would be able to much more accurately navigate your way down that hallway. And the ECM can do the same thing as far as making it down that hallway, staying at stoic or whatever mixture that it's shooting for at that time. And so that's the analogy between the two if we want to think about computer operation. And it's not perfect, I realize that, but it's a good way to think about the difference between operating with a narrowband and operating with a wideband sensor. Okay, so how do these things work? Now, I do want to make it clear that there are 4-wire versions and there are 5+ wire versions, meaning it can have 5 or more wires coming out of the sensor. And the 4-wire style do operate slightly different if you get down to the intricate details as the 5+ wires. But when we're looking at scan tool data and we're trying to understand these sensors, they're going to be similar enough in operation that we don't need to worry about the construction of the sensor. Now, if you're interested in this, there is a difference, and I'm going to provide some YouTube links in the show notes for this episode if you want to look into more detail on the difference between these two. Okay, but for audio only, when I have to describe this sensor with no pictures, it's going to be much easier if we just kind of consider these the same, even though there is some differences. So just want to make that clear. But we're going to dive into this as wideband sensors are the same because it will be easier to describe when there's no pictures and you just have to picture this in your head. So here's what I want you to do to try to understand how a wideband sensor works. Again, with no pictures. So we'll see how this goes. Maybe it'll go terribly. I don't know. Imagine in your head you have a narrowband oxygen sensor. And this is where it requires an understanding of a narrowband. And our goal, we're the PCM again, but our goal is to keep that narrowband oxygen sensor at stoic, meaning outputting a voltage of 0.45 volts or 450 millivolts. And we're going to do this by surrounding that narrowband with exhaust gas that reflects that, okay? So we're surrounding it with exhaust gases that reflect a stoichiometric mixture that came out of that combustion chamber, okay? So we have our narrowband, we just surround it. Our goal is to get an output of that sensor of 450 millivolts. We're to surround it with exhaust gas that reflects that. That's our goal, okay? But we only have access to exhaust gases that have exited the engine in the exhaust pipe. And as we know, it's rarely stoichiometric coming out of the engine. Especially there's so many variables that go into how the mixture is going to be, and that's even without a problem. And then you start introducing some issues, and of course you may have rich, you may have lean, but our goal remains the same. Our little narrow band that we have in this isolated chamber, we can surround it with exhaust gas, but we only have access to the exhaust gases that came out of the engine. But we still have to make that stoichiometric. So how are we going to do this? So what we're going to do is we have our narrow band with its little chamber surrounded by exhaust gas that we've filled with exhaust gas coming out of the engine. And we now need to change it. Let's say this mixture is 0.9, right? It's rich. There was too much fuel, not enough oxygen that went into the engine. We have a rich mixture, but we still want to get it down to stoic. We would actually pump some oxygen into that chamber around our narrow band from the exhaust. Now you might say, well, it's rich. How do we get exhaust? There's still some in there, but we would pump oxygen in until that number drops down to 0.45. Or let's say our number was lean. It was 0.1 volts or 100 millivolts, indicating a lean mixture came through that engine. In that case, we would pump oxygen out of our little chamber and then back into the exhaust. And that would bring that voltage up to 0.45. Now, if it's at 0.45, we don't do anything. We don't pump anything. We just leave it be and we're happy. All right. But depending on how much oxygen we either need to pump out or pump in, not just the direction, but the amount that we have to move either in and out of our imaginary chamber reflects how rich or how lean that mixture was. And that's our goal. That's the PCM's goal too of one of these sensors. We're keeping a narrow band happy at 0.45, and the amount of work that it takes to do that equals the air fuel mixture that came out of that engine. Okay. So that's my best way to describe it with no pictures. If you want some pictures because that didn't make any sense to you, check out the links that I have in the show notes. But that's essentially what we're going to be doing. And I want you to just at least have that concept of pumping oxygen either in or out. And the amount of oxygen being pumped in or out is what determines how rich or how lean that exhaust was, or how rich or how lean combustion was. Now, again, we have to remember that we are the engine computer in this case, and the engine computer is going to be the one pumping oxygen in and out, and it's going to use this doing current. And I want you to remember that that's an important part of a wideband sensor. This is really a current measuring system that we're going to be using with this. Now, it's a very, very small amount of current, which makes it difficult to do circuit tests on these things. We're talking like 4 to 8 milliamps, very, very small amount of current, but it's using current in order to determine the air-fuel ratio. And that's the big thing to remember about these sensors that is different from a narrowband sensor. Narrowband sensor, we're looking at a voltage output from the sensor. In a way we are with this one too, but really the determination that we're making about the air-fuel ratio is based off of the current that we're using to pump oxygen in or out a portion of this sensor. How much current and in which direction did we have to apply to the sensor? That correlates to an air-fuel ratio value that came out of that combustion chamber or went into the combustion chamber. Think about this like a mass airflow sensor. And a lot of us are familiar with our traditional hot wire style mass airflow sensor and how that works. That is a device where we have a heated element in the airstream, right? That's part of the mass airflow sensor. And the goal of the actual sensor is to keep that heated element above ambient temperature at a certain degree, a specific certain amount above ambient temperature. And it's going to use it. It's going to do that by sending current, again, a small amount, but it's going to send current to that element to keep it hot or hot to a certain point. Now, depending on the temperature of the air and the amount of air going past that element, the sensor will either have to send more or less current to keep it at a set temperature. And based off the amount of current that it sends, it correlates that to a value that equals the amount of air entering the engine. Okay. So if you need me to do a mass airflow one, we can do that too, but that's how a mass airflow sensor works. And it's not exactly, but it's similar in the method that we're using for a wideband sensor is we're measuring the current that's being used and applied to that sensor, not only the amount, but in what direction, what polarity determines the air-fuel ratio after combustion. Okay, so hopefully if you're familiar with mass airflows, that helps you. If you're not, maybe that made it more confusing, but let's continue on either way. Now, there are several different ways that our engine computers are going to display this current value on the scan tool to us as technicians. And this is where a lot of guys get hung up. I mean, number one, they don't understand how it works, but number two, they don't even know what they're looking at in the scan tool, so they can't correlate it. They don't have a reference to correlate it to mean anything in their heads. And that's where I want to kind of help you out here to help you understand what you're going to see in the scan tool that is reflecting the current draw of this sensor. Okay. Now, the first thing that might be there and is not on all of them, I can say this is not applied to all manufacturers, and maybe I should even back up before I jump into this, is the great thing about a narrowband sensor is we can apply it to everything. Everything that uses a narrowband zirconium oxygen sensor is exactly the same, except for maybe some bias voltages that are present and maybe some pulse width modulated heater circuits that are a little different, but the sensor operation it's same is identical. Whereas with a wideband sensor, we can't always do that. 0.9 doesn't always equal 0.9. 0.1 doesn't always equal 0.1 like it did with a narrowband. We've got a lot of variation here. And this is where being an educated technician really pays off, because not everybody can grasp all this stuff. Not everybody can get their head around all of these different variables that you run into when working with these sensors. But again, one of the first things you might see as a data PID, as a useful piece of information relating to this sensor and the scan tool, is the actual current draw. Okay, and I like that. I actually like to see what's actually happening with that sensor. Thank you for providing me with the real information, and it may show you in milliamps the amount of current that's being used to pump oxygen in or out of the sensor. Okay, and in this case, it will show you a positive or negative value, and in most cases, think about positive current as adding fuel and negative current as subtracting fuel, although that's not always the case. There's variations even on that. With a Honda, it could be opposite, but it will show you the polarity and the amount of current. And if you're familiar with the brand and the sensor, you could use that to your advantage. But that's actually what's happening with that sensor. It's measuring those milliamps for you, which is fantastic, because if you're going to try to do that yourself, not to say that you couldn't, but it's going to require some specialty equipment to measure 4 to 8 milliamps accurately, and have it be useful information. Whereas the PCM or the ECM in this case is already doing it for you. It's already measuring it. It has built-in circuitry to measure this, and it's going to show you as a scan tool data PID. All you got to do is plop your butt down in the seat, plug in a scan tool, and look at the value one direction or another. That's it. Easy. So I like it when that's there. I'm letting the scan tool do the work for me, or letting the ECM do the work for me. One thing I can say, and I would encourage you to try, if you have this value of in your scan tool as far as current goes, try graphing it. I've tried graphing this on some vehicles, and I could actually see what appears to be the same waveform as a traditional narrowband sensor, meaning that it switches rapidly between rich and lean and rich and lean and rich and lean just over stoichiometric, or just over zero current. Because remember, zero current would be perfect. That's what we want. We don't want to have to pump oxygen in or out. We want it at stoic, so zero is good. Zero is stoic, but it will go above and below and above and below at a steady RPM. And my guess is to feed the catalytic converter. I could be wrong on that because I'm kind of just speculating, but that would be my guess as to why it mimics that. But give it a try. Try graphing that voltage on a normal running vehicle and see what you see. Okay, so that's our first data PID. Our second data PID that you might see in addition or separate from this is a voltage. And I want you to be really careful with this one. This one's probably the trickiest one. Not that it's not usable, but you have to understand what it is. If you see a voltage data PID, and of course, these can range anywhere from 1 to 4 volts for different manufacturers. It's whatever voltage that manufacturer decided to use for this. It doesn't have to be a specific amount, like a narrowband, 0.1 to 0.9. That's not the case here. We could have 1 volt, we could have 2 volt, we could have 2.2, we could have 3.3, 3, 4 volts, whatever the manufacturer wanted to use. That's what could be there in the scan tool. Now, if that's not confusing enough, you have to figure out what the range is for the one you're working on. It's not necessarily a real voltage number, meaning that if you were to measure the circuit, you may not be able to correlate that voltage PID to anything that you see on the actual physical circuit of the sensor. Maybe something similar on the pumping circuit, but as it changes in your scan tool, it won't change on the circuit. So what is this? Why is this even in the scan tool? How is it even helpful to us? Well, they put this voltage data PID in here. Let's just go with 2 volts. I'm just going to pick a number. Remember, it can be different, but let's pick 2 volts from this sensor. Now, this voltage will change as the air-fuel ratio changes, meaning that if we go lean, we go a certain direction, change in voltage. If we go rich, we go the other way, change in voltage. Okay, so what this is reflecting, what this computer-generated voltage number is reflecting, is the current flow of the sensor. They just changed it to a voltage. Why? I don't know. Maybe because techs were used to voltage from O2 sensors, but just give us the real information. We'll figure this stuff out. But there are some applications where that's all they give you is this voltage data PID that is computer generated. Okay. And again, it might reflect what's there on the circuit, but if you scope one and have a scan tool in your other hand and you affect the engine rich or lean, they won't move at the same rate. Okay. That number is a reflection of the current draw of that sensor. So as long as you understand that, you can still use it. Okay. Now, here's the other confusing part. The voltages will move in the opposite direction of a narrowband sensor moves voltages, meaning that if the mixture goes lean, the number will go up. Okay. In a narrowband, if the mixture goes lean, the voltage goes down. Low is lean. That's what we always said. If the mixture goes rich, the voltage goes down, the opposite of a narrowband. So that makes it even more confusing. And I remember looking at one of these things the first time and I was so confused. I'm like, what is this voltage? What does it mean? Why is it going the opposite direction of what I would expect it to? Again, it's reflecting current flow of the sensor. And if you remember that, it can be more useful to you. But it is, as far as I'm concerned, the most confusing part about these sensors. But you might see that as a data PID is a computer-generated voltage. Just think of it as a reflection of current flow. Now, on to the third data PID, and this is lambda. Okay, and this is probably my favorite one to use if it's available. It's not available in everything. Again, why these are more difficult is because you have to learn the brand that you're working on. But if it's available, I want you to use lambda, or I would suggest that you use lambda to help you evaluate these sensors. Okay. So lambda is the ratio of oxygen actually present in the combustion chamber compared to the amount that should have been present for perfect combustion, right? So all of the air that would have been needed to oxidize all of the fuel that was in the cylinder, that's lambda. And if that's good, if that's exactly where they need it, it's 1. Okay, so if you look in your data PID and you see lambda 1, that means that engine is running at stoich. And what's even better about this data PID is it doesn't matter the fuel that you're using. Okay, because if we think of stoichiometric, that number can be different depending on the fuel source, right? Pure gasoline's 14.7 to 1, but what if we have 10 to 15% ethanol? What if we're running E85? What if it's some other fuel source that I'm not familiar with and I can't even tell you what the number is? It doesn't matter for lambda. The stoich number is going to change as far as air to fuel ratio, but I don't care. If I have lambda, it's always 1. Lambda is lambda. It doesn't matter the fuel source or the mixture. We're shooting for 1. under most conditions anyway. I realize there's hard acceleration and decel and things like that. But let's say we're shooting for stoich. We're shooting for lambda 1. Now, again, that's the perfect amount of air to match to the fuel. Okay, so as that number goes up, as lambda increases in value to 1.2, that would be more air, or that would be a lean mixture. If that number goes down below 1, 0.8, 0.9, 0.7, that would equal a rich mixture. And that's always the case, regardless of the freaking vehicle, okay? That's why I like things like a narrowband sensors, because we can apply them across the board to everything, okay? And all these things I'm telling you about the wideband that you can't, lambda is one that you can. Regardless of all the the details that are different brand and brand, we can still use lambda if it's a data PID to show us what's going on, because the lambda number, it's a conversion that the ECM made based off of the current draw of that sensor. That's what it's showing you, saying, okay, I pumped this much current in this direction to make the sensor happy, and now I'm giving you a value of lambda to reflect what it took to do that. Okay. Now, again, the sensor could be messed up or whatever and cause that number to be off, but that's the number we're going to look at because it is direct reflection of what's happening with that sensor. And I like to use lambda whenever I have it. It's an easy thing that I don't have to remember or look up. I just know I'm shooting for lambda 1. Above that's lean, below that's rich. That's it. So those are my main data PIDs that I look at if I'm directly looking at operation of the wideband sensor. Don't forget, of course, you have fuel trims. You can use those exactly the same as our narrowband sensor. Remember, the driver of fuel trims is our oxygen or wideband sensor. That's still the case here. So positive, adding fuel to correct for a lean condition, negative, taking fuel away to correct for a rich condition, all driven off of what's happening with that sensor. Okay, so we can still use fuel trims, and I still do. I love fuel trims. They're one of the best tools for diagnosing drivability problems in an engine. We can also still compare the downstream sensor to our upstream. That's a big one still. If we're questioning the accuracy of the upstream sensor, is this telling us the right number? It's saying that the mixture is lean, like extremely lean, and it's adding a bunch of fuel. Well, let's look at our downstream and see, does that reflect that? And it should reflect that, right? We can't have anything, we can't have a different amount of oxygen entering the cat than would be exiting it. So we can always compare to the downstream, and that's where understanding a narrowband sensor operation would come into play. And finally, we don't want to forget about the heaters as well. We could look at the data PIDs for heaters. There's amperage draw and heater function, resistance on some applications. It's hot as a narrowband sensor. They have to be that to operate. So if the heater is not functioning, the sensor won't operate. And it's one of the things, of course, you want to check before you replace them is the heater actually functioning the way it's supposed to? And of course, testing the heater circuits really is no different than a narrowband. Most of them will be pulse width modulated, but we can test them the same way as we have always. It's just a 2-wire power and ground circuit that heats up an element in the sensor. A response test is another way that we can test these sensors to see if they're functioning properly, meaning forcing the engine rich or lean in one direction manually, applying propane, creating a vacuum leak, snap throttle, hard acceleration, deceleration, creating a mixture that we know is present in the intake manifold going in the combustion chamber going into the cylinder. Does our O2 sensor reflect that? That's a response test. We just want to make sure that it responds in the correct direction. That would be a way to test these. Now, of course, there's more circuits involved with these sensors, especially the 5 or 6 wire ones that you see. And that is one area where it does get a little tricky because the circuitry is going to be different for the sensing portion depending on the application. So I can't give you details on circuit testing here. What I can tell you is that the ones that I have dealt with, I've gone through the DTC lists and they have a lot of different circuit specific codes for these sensors. So hopefully whatever you're working on, if you get a circuit code for one of these, you're able to look into it, you're able to look at the diagram and then do some testing based off of that. Let your codes guide you to where you're going if there's a circuit issue. But looks like to me, at least most manufacturers are monitoring these circuits for integrity, and there will be codes if there's an issue. Because that would really be the hang up, is like, well, how do I know that the circuit's good to the sensor? You're going to be relying on the internal circuitry of the ECM in a lot of cases. Not to say that you couldn't figure out how to do a circuit test, but I can say that I haven't had to do any just yet. So maybe I haven't run into one that's had that issue yet, but most of the time it either ends up being a sensor issue or potentially some sort of engine air-fuel ratio problem that's causing codes. But that is pretty much all that I've got for wideband oxygen sensors. And there's probably more to it than that, but that's everything that I think that you need to know to go out there and start looking at these things and understanding them. But if you have any more questions, please let me know. Or if you know more about this and you know something that I left out of this, please reach out to me. I'd really appreciate it. But other than that, I just want to thank everybody for listening, everybody for reaching out to me that has reached out to me. Really appreciate it. So with that said, let's all get out there, start fixing the world one car at a time.